What if I told you that light which should be swallowed forever by a black hole has been seen coming from the other side? That's right, from behind a black hole, in a region so twisted by gravity that the very laws of physics seem to unravel. For centuries we believed that the event horizon was an absolute boundary. Cross it and there's no return. But something extraordinary has happened. NASA scientists, using the Chandra X-ray Observatory, along with the European Space Agency's Newton Space Telescope, have just done what was once considered unthinkable. They've detected actual light X-ray emissions from the far side of a black hole thanks to the warping of space-time itself. Let's break that down. We're not talking about a black hole a few hundred kilometers across. This one sits in the heart of a galaxy called Zwicky 1, a swirling colossus more than 800 million light-years away from Earth. At its core is a supermassive black hole millions of times more massive than our Sun. Matter falling into it forms a glowing disk known as an accretion disk, a violent maelstrom of gas, dust, and energy spiraling at nearly the speed of light. Friction and gravitational shear heat this material to extreme temperatures, reaching tens of millions of degrees Celsius and emitting intense X-rays. Normally, the story ends there. These X-rays either shoot out into space or vanish into the black hole's shadow. But here's where it gets fascinating. When a flare occurs in the accretion disk, think of it like a cosmic lightning strike. It releases a burst of X-rays. Some of that light heads straight toward us, but a fraction of it located just behind the black hole shouldn't be visible at all. It should be lost. Yet Einstein's general theory of relativity tells us that massive objects warp the fabric of space-time. That warping can bend the path of light around an object much like a lens. Now imagine this. Light emitted from the back of the black hole doesn't travel in a straight line. Instead, it loops around the black hole's gravity well, like a spacecraft performing a gravity assist maneuver around a planet, and emerges from the other side, aimed directly at Earth. This is gravitational lensing in its most extreme form, and for the first time, scientists were able to detect this looped light not from a galaxy or a star, but from a black hole itself. Here's what makes this even more stunning. The photons that reached us from behind the black hole were faint, echoes of the original flare. They arrived milliseconds after the direct light, and they were reflected off the inner edge of the accretion disk, a region that lies incredibly close to the event horizon. This isn't light from behind, in the way we normally think of reflections. This is light whose path was curved through space-time in a gravitational slingshot, showing us the back of the black hole without ever physically going there. And the implications. Mind-bending. For decades, black holes were thought to be the ultimate cosmic cul-de-sacs, a one-way trip. But now we have evidence that even their backsides, obscured by a silhouette of warped geometry, can be observed under just the right conditions. Einstein predicted this a century ago in equations so complex that even he wasn't fully sure how far they would reach. This detection not only confirms his predictions with eerie accuracy, it opens the door to studying environments previously thought inaccessible. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. So how did the team manage to separate these ghostly echoes from all the noise? Think of the black hole as a cosmic stage. You have direct spotlights, bright X-ray emissions that shine toward Earth. But then, you have hidden echoes bouncing through the twisted theater of space-time. Using extremely precise X-ray timing data, scientists at Stanford University, led by astrophysicist Dan Wilkins, analyzed these echoes and determined that they came from the opposite side of the black hole. Wilkins described it as observing the same flare twice, once directly and once through a warped, time-delayed lens. The flare originated from something called the corona, a mysterious region of high-energy electrons above the accretion disk. Scientists believe the corona is where magnetic fields twist and snap, launching bursts of energy that light up the surroundings in X-rays. After the flare, some X-rays hit the accretion disk and were re-emitted, including those from behind the black hole. When that light curved back around, It gave researchers their first peek at something no human has ever seen, the backside of a black hole, revealed not by sight, but by the distortion of space itself. It's important to realize that this is not a loophole in black hole physics. No laws are being broken. The light we're seeing did not emerge from within the event horizon. That's still an unbreakable boundary. What we're seeing is light that narrowly escaped, skimming just outside that deadly line, bent by gravity's hand until it reappeared in our view. It's like seeing a reflection in a funhouse mirror, except the mirror is space itself, and the distortion is reality. Now, we'll peel back the curtain on how these astonishing signals were isolated from billions of competing sources in the X-ray sky. We'll also explore the implications this has for understanding black hole spin, accretion dynamics, and the deeper mysteries of quantum gravity. Are we standing on the edge of the next revolution in astrophysics? Stay with us. To truly grasp the magnitude of what NASA has uncovered, we need to go deeper, not just into space, but into the data. Because this wasn't a one-off flash caught by accident. This was the result of years of meticulous planning, data collection, and analytical precision, all aimed at confirming one of the strangest and most beautiful predictions ever made by Einstein's general theory of relativity. What the scientists captured wasn't just light from behind a black hole. It was the timing of that light, the echo of a cosmic heartbeat delayed ever so slightly by a detour through warped space-time. Let's return to our scene. A black hole, billions of kilometers across, spinning at nearly the speed of light, its immense gravity twisting space and time into a funnel so deep it might as well open into another universe. Orbiting near its edge is an accretion disk, an inferno of superheated matter spiraling inward. Suspended above this disk, like a ghostly halo, is the corona, a region of ultra-hot electrons producing X-rays so intense that they momentarily overpower everything else around them. This is where the flare began. The flare, when it erupted, released a surge of X-ray photons in all directions. Some of those photons shot straight toward Earth, arriving at our telescopes and triggering a sharp spike in the data. But others took a more circuitous route. They traveled downward, struck the inner edge of the accretion disk and were reflected, some forward, some backward, and some sideways. A portion of those backward-moving photons curved around the back of the black hole, riding the bent contours of space-time until milliseconds later, they emerged on the other side and journeyed onward to Earth. This delay, this minuscule difference in arrival time, is the signature scientists were hunting for. But how do you find such whispers in a storm? The X-ray sky is a noisy place. From pulsars to supernova remnants to distant quasars, space is teeming with high-energy phenomena. So on top of that, Chandra and XMM Newton are constantly bombarded with cosmic rays, solar radiation, and instrumental noise. Isolating these echoes from that chaos is like trying to hear a single violin note in the middle of a stadium. Rock concert enter Dan Wilkins and his team. They designed an experiment that would treat the corona flare as a kind of cosmic sonar pulse. First, they modeled what the direct signal should look like: sharp, immediate, and brief. Then they searched for signals that looked almost identical, but slightly delayed, slightly fainter, and with energy signatures suggesting they had bounced off the accretion disk. They used a technique called reverberation mapping, which measures the time lag between the primary flare and the echo. If the flare was a clap of thunder, these delayed signals were the faint echoes off canyon walls, billions of light-years away. The team observed that the echoes not only matched in timing, but also showed a redshift, an energy drop consistent with the photon's journey through intense gravitational fields. That redshift wasn't just a footnote, it was proof that the light had been pulled deeper into the black hole's gravitational well and then flung outward. The delay was also precise, a few milliseconds, but exactly what models predicted for light, curving around the far side of the black hole. This is more than a beautiful confirmation of Einstein's equations. It's a tool, a new way of probing the anatomy of a black hole. These echoes tell us about the structure of the corona, the inner edge of the accretion disk, and even the spin of the black hole itself. A spinning black hole, known as a Kerr black hole, drags space-time around with it, a phenomenon called frame dragging. The faster it spins, the closer the accretion disk can orbit without falling in. By studying the echo patterns, scientists can estimate how fast the black hole is rotating, how tightly it's winding space-time, and how close the disk gets to oblivion before crossing the event horizon. And here's where it gets even more intriguing. The corona's very nature remains a mystery. Is it a cloud of particles, a tangle of magnetic fields, a burst of quantum energy? By measuring how the X-rays bounce, scatter, and shift in frequency, we're beginning to see it not as a vague tableau, but as a defined region with depth, shape, and motion. Some researchers believe the corona is formed by magnetic reconnection, where magnetic fields snap and rejoin, flinging energy outward in explosive bursts. That same process happens in solar flares on the Sun, but in the environment of a black hole, it becomes supercharged and relativistic. This kind of detailed observation wasn't possible even a decade ago. It required the combined precision of Chandra's sharp X-ray vision and Newton's deep energy sensitivity. It also required long observation times, hours spent staring at a single target, waiting for the flare, then analyzing terabytes of data for patterns so faint they could be lost in digital rounding errors. And yet, here we are. We've not only seen the flare, we've seen its shadowy echo. We've mapped a piece of the unseeable. For the first time, light from the far side of a black hole has been observed not just as a trick of lensing, but as a measurable, time-stamped signal. It's like decoding a message bounced off a wall we were told we'd never even be able to touch. There's something undeniably haunting about black holes. Not just because of what they are, cosmic gulfs that devour everything, even light, but because of what they represent, the boundaries of human understanding. They are the places where our most trusted theories, our most elegant equations, break. And now with the detection of light from behind a black hole, we are peeking through a crack in the cosmic curtain. And what lies beyond may challenge the very framework of physics itself. Let's rewind for a moment. At the heart of this story is a paradox that has confounded physicists for decades. What happens to information that falls into a black hole? According to classical physics, particularly general relativity, anything that crosses the event horizon is gone forever. The black hole grows in mass, but the specific details about what fell in, whether it was a star, a spaceship, or your favorite playlist, are lost. It's just mass, charge, and spin, nothing more. But that directly contradicts quantum mechanics, which insists that information cannot be destroyed. Ever. This is known as the black hole information paradox, and it's one of the deepest mysteries in modern physics. Now, let's connect the dots. What if, just what if, these newly detected X-ray echoes, bent and delayed by gravity, carry more than light? What if they carry traces of information from their source, clues about the matter and energy that produced them? We're not talking about data packets or readable code, but subtle imprints, tiny changes in frequency, direction, or polarization that might, in theory, encode quantum information. Some physicists believe these echoes could be the beginnings of a solution, a way for black holes to communicate without breaking the laws of physics. One theoretical framework gaining traction is the holographic principle. It suggests that everything inside a black hole, the three-dimensional reality, is actually encoded on its two-dimensional surface, the event horizon, like a cosmic hard drive. If this is true, then the echoes we're detecting may not be just reflections of light, but reflections of the surface data of the black hole itself. In other words, we're not looking through the black hole. We're looking at the information it stores, bent around by gravity, revealing its secrets in echoes and shadows. But there's another layer here. These observations also give us rare access to one of the most extreme laboratories in the universe, the warped geometry of space-time near the event horizon. You see, in most regions of the cosmos, general relativity and quantum mechanics play nicely in their own domains, but in the crucible of a black hole, they collide. Gravity becomes so strong, curvature so intense, that quantum effects can no longer be ignored. The result? A place where particles flicker into existence and vanish, where time slows to a crawl, where space is stretched and crushed into unimaginable forms. When the X-ray flare erupted and its echo curved around the black hole, it passed through this twilight zone, this region of maximal distortion, and the light that emerged was changed, not just in energy but in structure. It carried embedded within its photons the story of that journey, and when we detect that light on Earth, we're not just seeing a flare, we're seeing a map of space-time. Under the most extreme conditions known to science, this opens the door to something breathtaking, testing the very fabric of reality. With each observation, we refine our models of black hole geometry. We begin to see whether Einstein's equations still hold up under these pressures, or whether tiny deviations, small inconsistencies, might hint at a deeper theory. Something beyond relativity, something like quantum gravity. Quantum gravity has been the holy grail of physics for nearly a century. String theory, loop quantum gravity, emergent gravity. Each has its champions, and each attempts to unify the smooth, continuous world of relativity with the pixelated, probabilistic world of quantum mechanics. But until now, we lacked the observational tools to test them. Black holes were thought to be observationally sterile, too dark, too far, too chaotic. But now, with these gravitationally bent echoes of light, we may have our first probe into that realm. And let's not forget the poetic side of all this. Imagine it. A flare erupts in a maelstrom of death and fire above a black hole's spinning maw. Its light races away, some directly, some bending, some diving deep into the gravitational well, circling behind the very object meant to erase it. And then it escapes. It curves around and whispers its story across 800 million light-years of empty space. That whisper reaches us, just a few photons out of billions, and we catch it, decode it. And in that decoding we touch something truly profound, the edges of reality. Of course, there are still skeptics. Some physicists warn that we must be cautious. Echoes like this could, in rare cases, be mimicked by other astrophysical phenomena. X-ray reflection off disk material, for instance, or complex magnetic interactions in the corona. But the timing, the energy shifts, the alignment with relativistic predictions, all these point squarely to one cause: light bent around the back of a black hole, exactly as Einstein foresaw. Still, one can't help but wonder, what else might be lurking in these echoes? Could further observations reveal patterns, structures, or anomalies that standard models can't explain? Could we, in time, discover that black holes are not just endpoints of stars, but gateways to deeper physics? Perhaps even other regions of space or parallel timelines? There's something deeply humbling about chasing the light from a place where even light shouldn't escape. Something poetic. We're used to stars, galaxies, even the edge of the observable universe speaking to us in photons. But black holes, they were the universe's ultimate mute witnesses, until now. With the echoes of light bending around their backs, we've crossed a threshold not just of detection, but of understanding. And perhaps, just perhaps, of something far more profound. Because what we've uncovered isn't just a quirky cosmic illusion or a trick of light. It's a message written in the geometry of space and time, in the warping of reality itself. The fact that we've seen light echo from behind a black hole isn't just a confirmation of Einstein's century-old predictions. It's a signal that the universe still has stories left to tell. Stories hidden in the shadows, and now those shadows are beginning to speak. So what happens next? Well, this is where the future becomes exhilarating, because NASA's observation, combined with the capabilities of Chandra and XMM, Newton, has set the stage for a new era of astrophysics, one where we don't just observe black holes from afar, but actively listen to them through their echoes. And we're not stopping with just one detection. This discovery is pushing scientists to comb through archives of X-ray data, searching for similar echoes from other black holes. Some are now convinced this phenomenon might be more common than we thought. We simply hadn't known where or how to look. Even more exciting is what's coming next. The European Space Agency's Athena X-ray Observatory, scheduled for launch in the early 2030s, will carry technology orders of magnitude more sensitive than what we have now. Its instruments will be capable of not just detecting these flares and echoes, but resolving them in exquisite detail, potentially identifying variations in polarization, frequency drift, and even quantum interference patterns. What we've seen so far is the opening note of a symphony. Athena could let us hear the entire score. And then there's the Lynx X-ray Observatory, a proposed NASA mission that could change everything. Lynx aims to be hundreds of times more sensitive than Chandra. With its ability to image faint echoes across vast stretches of space-time, it could turn black holes into observable laboratories, giving us insight into particle acceleration, magnetic field dynamics, and the nature of quantum space-time itself. Some even speculate that Lynx might allow us to detect echoes from primordial black holes, those thought to have formed just moments after the Big Bang. But the implications go even deeper than technology. Because every time we uncover something new about black holes, we're not just learning about the objects themselves, we're learning about the rules that govern the universe. And when those rules bend or break, we find the clues to something bigger. The fact that photons can loop around a black hole and escape speaks volumes about the underlying architecture of spacetime. It hints at hidden symmetries, maybe even hidden dimensions, and that raises the question no one can resist. What else might be hiding behind that veil? For decades, scientists have speculated about the existence of wormholes, tunnels through space-time that could, in theory, connect distant parts of the universe. Some believe rotating black holes, or Kerr black holes, might contain the ingredients for such passageways. If light can orbit and echo from the far side of a black hole, what else might escape? Could gravitational waves, warped and twisted in just the right way, carry with them messages from inside? Could entangled particles somehow maintain their link across the event horizon? These are still questions of theory, but no longer of pure theory, because now we have data. We've moved from black holes being conceptual endpoints, cosmic, terminators of matter and light, to being gateways into new physics. They're no longer just the great destroyers, they're becoming the great revealers. And it goes beyond physics. There's something about this discovery that touches on something human. To detect light from behind a black hole is to say, even in the darkest corners of the universe, light finds a way. That truth, as poetic as it is scientific, resonates in a world where we're constantly searching, through telescopes, equations, and imagination, for meaning in the cosmos. So now the question isn't if we'll find more echoes, it's when. And as we prepare for the next generation of observatories, theories, and debates, we stand at the edge of a new frontier, a place where gravity, time, and light dance in a way we're only just beginning to understand. We've heard the echo. Now it's time to listen closer. If this journey into the shadowy heart of a black hole sparked your imagination, share this video with someone who loves the mysteries of space. Drop your thoughts in the comments. What do you think these echoes are telling us? Are we hearing the voice of Einstein's universe, or whispers from a deeper, hidden reality? And if the cosmos continues to echo, you'll find us right here at Cosmic Whispers, ready to listen with you. Until next time, keep looking up.